Okay, so today in section 4 of chapter 3, we are looking at perpendicular lines. So you'll have to pause the video and try this and come back when you're ready to check your answer. But who's done already? Are you all done? Okay, so number 1, x minus 5 is less than 8. So we can say together x is, good, x is less than 13. Okay, so we simply use what property here to isolate x?
Addition.
Property of equality, good. And then here, oh, we got x's on both sides. Yeah, addition, property of inequality in this case, that. Okay, so here we got to move the x over and so on. And what do you have, Andrew? X is?
X is greater than half.
So, all right, does your sign look like this? Or is it reversed?
It's reversed.
Okay, so did you subtract 3x from both sides?
No, I subtracted
X,
X from that side.
1.
I mean, negative 1/2.
So say it one more time. X is,
Greater than negative 1/2.
it's actually, oh, it's great. Well, you're right. Let's see.
Because when you,
You're not dividing by a negative. This is 2,
no,
right?
you divide it by 2.
Yeah, but when you divide by a positive, you don't switch a sign. So let me just see. Subtracting that gives you 2, right? Subtracting 1 gives you negative. Right? And that doesn't reverse the sign. And so then you divide by 2, and this should be less than then.
I said less than.
Okay, let me work this out. Okay, so 3x plus 1 is, they say, less than x. So if we subtract an x from each side, that does not reverse the sign. 2x plus 1 is less than 1. Subtract 1 from each side, that does not reverse the sign, right? Divide by 2, that does not reverse the sign. X is less than negative 1/2. The sign is wrong. And we see this sometimes in this book. You know, so there you go. It should be x is less than negative 1/2. And number 3, together, y equals, good, y equals 18. Number 4, not hard, x equals
15.
good. And then solving the system, you have 2 choices. Well, anyway, oh, this is such a baby equation, huh?
X equals 10.
Y equals what?
15.
And then you just substitute, and x equals 10. Good. Okay, so today we're going to prove and apply theorems about perpendicular lines. But perpendicular rather than parallel. If we have well, the theme of today, perpendicular. So if we have a perpendicular bisector, what can we say? If a line bisects or a segment bisects another segment, what can we say? A bisector actually cuts another segment in a perfect half, okay? So when you see that word bisector, think half. Just like an angle bisector will divide an angle into 2 congruent smaller angles, right? So a perpendicular bisector will bisect a segment at its midpoint. The shortest distance from a point to a segment is a perpendicular segment. Okay, so from any point to another segment, let me put a segment on the board. So here's a segment, and if we take any point out here, any point, the shortest distance now to this segment will always be, you understand, a perpendicular segment. I mean, it wouldn't be shorter for me if I go from this point A to this segment down here. You know, going straight to it, forming a right angle, is going to be the shortest segment. If I go just ever so slightly to the left, you see that that segment's longer than the perpendicular segment. So that's what that's saying. Okay? So let's name the shortest segment from point A to line BC. And so name that for us, Andrew.
It's
AP, so that's pretty easily given here, okay? So now we want to, what do we want to do here? We just said that the shortest distance from A to this line CB would be a perpendicular distance, right? So if that's true, then AP is the shortest segment from A to that line, right? But when we look at x minus 8, we have another segment that is going from point A to line CB. But is it the shortest segment?
No.
So how do these 2 segments compare? AP and AC. AP is less than AC, right? So rather than using the Pythagorean theorem, we can't really solve, we don't know this other side CP, but we can show a relationship between 12 and x minus 8, right?
So 12
Because 12 must be less than x minus 8. So the way that we can show that kind of in a proof style is AC must be greater than AP, right? That's given that AP is the shortest segment. And so now we can substitute into this, right? What we know about AC, which is x minus 8, and AP is 12. That's just substitution of the given information. And now here we are back to what you were just doing. We can isolate x, right? And when we do, we can say that x is what, Matthew? So we're adding to both sides, and x is greater than 20. Very good. So we were making it a little more complicated, thinking we should use Pythagorean, but I'm glad you're thinking that way, because whenever you see a right triangle, you want to be thinking Pythagorean theorem, so that's good. But this is simply a case of comparing this perpendicular segment and this one that's not perpendicular. Okay? Okay, so let's do it again, and come back and check your work real quick. So Kaylin, give me your justification. Well, first of all, what's the shortest segment?
AB.
Good, AB. And now what would the first step be?
AB is less than AC.
Good. They wrote it as AC is greater than AB, same thing, right? They just have the whole thing turned around. And that's really, it's given this, right? Given that a perpendicular segment is the shortest segment. They didn't say that over here either. But it's due to the fact that it's perpendicular to line BC. Okay, so go ahead, Kaylin, what do we say next?
And then you substitute in x minus 5 is less than 12.
Good, or 12 is greater than x minus 5, and that's just substitution.
And then you add 5 to both sides.
Good, add 5 to both sides, and you would call that
Addition.
the equality, and they just say add 5, okay, and you get x is
17. Or wait, x is greater, or less than 17.
x is less than 17, or 17 is greater than x. Good, very good. Okay, that was not hard, was it? Yeah, we do. We go into other things, but let's try this now. Pause and come back and check your work. Okay, so how about number 1, Sydney? Okay, good. And number 2, you had to find the value of x and y. Who has it already? Andrew, what do you have? Good, and so x equals 9 because,
And that's, well, it has to equals 90 because, it's supplement,
good. Good. So x equals 9 because we know that if this is a 90-degree angle, that this is a 90-degree angle. This is a corresponding angle too, to a 90-degree angle. So if x equals 9, we can simply substitute that here, and this entire expression equals 90 as well, right?
If there wasn't,
Oh, that it was. Okay, so these little arrowheads prove that we have parallel lines here, so now we know that these are corresponding angles, right? Without that, without these two lines here, even if it looks parallel, we can't say that it's given that it's parallel. This is given that it's parallel because of those arrowheads. Good. Okay, so here are some theorems that we're going to use in proving some statements ahead, and they have to do with our perpendicular lines. So the first theorem is if two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So if we have a linear pair of congruent angles, what is the measure of each angle? Because a linear pair forms supplementary angles, right? So we're talking, without saying it, we're talking about two right angles, two 90-degree angles, okay? The second one says there's some sort of a transversal theorem. It says in a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other. So what type of a transversal is this? Perpendicular transversal theorem. So if we know that the lines are parallel and the transversal is perpendicular to line N, the transversal must be perpendicular to line P. And then finally, if two coplanar lines are perpendicular to the same line, do you see this? Then the two lines are parallel to each other. So in this case, we're proving that these lines are parallel by what theorem? Good, converse of the corresponding angles theorem. This is kind of a repeat. In this case, the two corresponding angles are right angles. So we're showing they wouldn't even have to be right to prove that these are parallel, but in this case they are, okay? And we know that it's a perpendicular transversal. Okay, so let's try some proofs with this information here. So in this case, line 1, Kaylin, what will the first statement be?
R is parallel to S, and angle 1 is congruent to angle.
Yay, we always love the first statement, don't we? Because it is given. Okay. We know the last statement too. Do we want to fill that in? It's nice to fill it in.
I always do that first.
So we know, what is it, Michael?
R is parallel, or
Perpendicular to T. But we don't know why yet. We've got to know what is going on in statement 3. So given that R is parallel to S and angle 1 is congruent to 2, what would we like to say next? We're trying to prove that R is perpendicular to T. So what do you want to prove up here?
2 is congruent to 3.
What would you really love to prove, though? She says 2 is congruent to 3. Well, we might use that as a stepping stone to get there, but we really want to prove 1 is congruent to 3, right? Because if we can say that, we can say that they are right angles, right? Since they're forming a linear pair. Okay? So given that 1 is congruent to 2, what do you want to say next? Okay, he says, because R and S are parallel, that was given, we can say that 2 and 3 are congruent. Very good. And that's based on what?
Actually, everything.
Well, not, but we're doing it step by step. So 2 and 3 are congruent. Why, Matthew? Corresponding angles. That's right. Okay. So we know that 1 and 2 are congruent. We know that 2 and 3 are congruent. So what can we say now, everyone? 1 and 3 are congruent based on transitive property of congruency. Good job. And now that we know that 1 and 3, we've proven that 1 and 3 are congruent, we can say that R is perpendicular to T based on this step. What happened in this step? This proves it because, which is two intersecting lines form a linear pair of congruent angles, so therefore the lines are perpendicular. The way that they state it here is perpendicular transversal theorem. Let's see. We could have used that as well. That would have worked there. When you do spend that effort to really understand these, it will make a brand new proof much nicer for you. So give us the first step here, Kaylin.
Angle EHF is congruent to angle HFG.
Did I call on you last time too? Oh, look at, we're only putting that here. And you're right, that's given. Okay? So usually when we don't have both of the given pieces on the first statement, then we don't see the next, we don't see this other given one yet, right? We usually see that maybe step 3 probably, right? So, Sydney, what might we say flowing from the fact that these two angles are congruent? EHF and HFG. This one and this one. So she's saying EH and FG must be parallel. That flows from there. Good. And that's based on what? Converse of the alternate interior angles theorem. Good job. Okay? And so we now know that EH and FG are parallel. So now we might go up and take this other piece of given, right? FG is perpendicular to GH. It's given. So if we know that these are parallel and FG is perpendicular to GH, what we now are going to say is EH is perpendicular to GH, right? Which is what we were setting out to prove based on what statement, Michael? What reason? If FG is perpendicular to GH and FG and EH are parallel, we can say that EH is perpendicular to GH based on, anybody else? It was that perpendicular transversal theorem. It was the very theorem. If we find that we have parallel lines and a transversal is perpendicular to one of the parallel lines, it will be perpendicular to the other one. That is the perpendicular transversal theorem. Okay? Okay. This is just an applied real world problem. You know, here in this, we should be able to relate to it as a rip current. Has anybody been caught in a rip current here? Okay, so you know it's pulling you straight out, right? It's like a river flowing straight out from the beach. And so you've probably been taught what to do. What do you do if you want to swim out of it? It's like you got to get out of the river and then you can come back in where you're not in that current. It's hard to swim up a river. It's really hard. The current is just coming very strongly that way, which is what a rip current does. So a swimmer who gets caught in a rip current should swim in a direction perpendicular to the current. Here's the current, perpendicular. Why should the path of the swimmer be parallel to the shore? Why should the path of the swimmer be parallel to the shore? Because if you're parallel to the shore, you are perpendicular to the current. That's right. Okay? So there you go. If you are parallel to the shore, you are perpendicular to the current. Okay? Go ahead and try this, and we'll check it. This one feels very much like that other one we did. As I'm looking at it, Andrew, what's the first statement you would give?
Angle 1 is angle 2.
Good. And that's given. So what flows from that, if angle 1 is congruent to angle 2?
R is parallel to
Good. R is parallel to Q based on what?
the converse corresponding angles.
Actually, it's 1 and 2. Oh, 1 and 2 are out here. You're right. It's the converse of the corresponding angles. Okay? And so now we would say what? Good. The other piece of given information, and that was given. And so we're setting out to prove statement 4. P is perpendicular to R. And we can say that by, if P is perpendicular, right, it is. The perpendicular transversal theorem. Very good. And here's your assignment right here. And have fun.